Forget what you think you know about computers. Quantum computing is here, and it's about to change the world as we know it. Get ready for a mind-blowing journey through the history of this groundbreaking technology and discover its potential to shape our future. Quantum computing is not just science fiction anymore. This technology has the potential to revolutionize everything from medicine to artificial intelligence. Join me as we delve into the history of quantum computing and explore its incredible future possibilities. My fascination with quantum computing began with a simple question: how can we solve problems that are impossible for even the most powerful computers today? Join me as I explore the journey of quantum computing, from its theoretical roots to its potential to unlock the mysteries of the universe. Quantum computing was conceived in the early 1980s when Richard Feynman observed that classical machines struggle to simulate quantum behavior and proposed building computers that themselves follow quantum rules. His 1981 lecture, Simulating Physics with Computers, planted the seed for the field. 4 years later, David Deutsch proved that a universal quantum computer could, in principle, outperform any classical device, giving the discipline a solid theoretical foundation. With that groundwork laid, researchers began designing algorithms that could exploit quantum weirdness. In 1994, Peter Shor showed that a sufficiently large quantum computer could factor large integers exponentially faster than any known classical algorithm, threatening the RSA crypto system that still secures much of today's internet. 2 years later, Grover demonstrated a quadratic speedup for unstructured search problems, proving that quantum advantage was not limited to niche number theory. Theory leapt into the laboratory at the turn of the millennium. Using 7 nuclear spins in a specially prepared molecule, an IBM-led team executed Shor's algorithm and factored the number 15 in 2001, hardly a practical calculation, yet dramatic proof that qubits could be tamed long enough to run a real quantum circuit. What makes those qubits special is their ability to exist in superposition, like a spinning coin that is both heads and tails, until you look, and to share correlations called entanglement, so that measuring one instantly reveals something about its partner, no matter how far apart they are. While a classical n-bit register describes just one of second possible states at a time, an n-qubit register embodies all second states simultaneously. Quantum algorithms choreograph interference among those parallel paths, amplifying the right answers and canceling the wrong ones. Today's race is to build hardware stable enough and large enough to run those algorithms at scale. In the superconducting camp, IBM plans to debut its 1,386-qubit Kookaburra tile in 2025 and link 3 of them into a 4,158-qubit quantum-centric supercomputer, edging closer to fault-tolerant territory. Google has already shown that error-corrected logical qubits can improve as they scale. Its 101-qubit Willow chip achieved a distance 7 surface code memory with an error rate below the break-even threshold, the first time error correction has actually reduced logical errors on hardware. Other architectures are advancing just as rapidly. IonQ's trapped ion Forte Enterprise, launched worldwide in March 2025 via Amazon Breakit, offers 64 algorithmic qubits ions, whose long coherence times make them ideal for deep circuits, even if gates are slower. Neutral atom arrays have come of age too. Quera's 256-qubit Aquila processor arranges rubidium atoms like checkers on a board and moves them with lasers to execute logic. Meanwhile, photonics specialist PsiQuantum has secured public-private deals to build utility-scale million-qubit photonic machines, betting that light-based qubits and semiconductor foundries will scale faster than cryogenic metal circuits. Why fight for so many qubits? Because the most tantalizing applications, accurate molecular modeling, combinatorial optimization, and advanced machine learning, quickly overwhelm today's modest devices. Hybrid quantum classical workflows have already begun to attack genuine drug design problems, using quantum subroutines to evaluate binding energies that classical simulations approximate only crudely. Early quantum machine learning pilots are optimizing financial portfolios, delivery routes, and even climate model ensembles, signaling a shift from pure theory to practical impact. Materials science is another frontier. Quantum-assisted algorithms are improving battery chemistry simulations, vital for next-generation electric vehicles. Governments see the strategic stakes. The United Kingdom, for example, has committed hundreds of millions of pounds to ensure sovereign access to quantum computing, joining similar initiatives in the United States, Europe, and Asia. Yet even with deep pockets, the community must still conquer decoherence. New low-density parity-check error-correcting codes promise lower overheads than the ubiquitous surface code, but they still require physical error rates, well below 1% and thousands of helper qubits for every robust logical qubit. The path ahead, therefore, pairs audacious engineering with careful algorithmic pruning, squeezing more mileage from each qubit while wafer-scale fabrication, cryogenics, and photonics race to supply millions more. If those efforts succeed, quantum computers will become not just faster calculators, but entirely new microscopes on nature, able to peer inside molecules, markets, and materials with a clarity classical bits can never match. Mastering that capability will demand new skills, quantum-safe encryption, and an open, curious mindset. But the reward could be a step change in innovation and economic growth. The quantum era, once a physicist's thought experiment, is fast becoming a practical tool, and the story is only beginning to unfold. If you enjoyed this video, give it a thumbs up and let me know your thoughts in the comments below. Don't forget to hit that subscribe button so you never miss the next upload. Share this with a friend, and I'll see you in the next one.